Hello there. Welcome to another mini lecture on this time on circular motion. So, in circular motion, you already kind of can tell that there will be some constraint in how things move, right? So, you have a circle. It can be anywhere, and it can be like a vertical circle, or it could be horizontal circle, or it can be circle at an angle. So, but this is circle. So this is radius r, radius r, radius r. So can we circle in space? Circle near Earth. So here is an Earth, and something is kind of moving in a circle above Earth. So here is the sun, and maybe Earth is moving Earth-Sun distance. Here's Earth, and here's the sun. So many examples of this. You can have a star A, another star B, and this is the center of mass, and this going in a circle around the center of mass, and this going in a larger circle about the center of mass, like that. So this is fixed, and this is going, and this guy is going maybe opposite direction. So maybe when it's here, and that guy is over there, not over there. So at t equals 0 is here, and at t equals t it's over there. So t equal to 0 is here, and t equal to 0 is here, and t is here, exactly opposite over there. So they're rotating opposite to each other, but they're going in circles. So many examples of circle. So in all of this, you have the radius of the circle. So we'll draw the radius of the circle in, we will draw in some xy plane, just to be specific. Don't need it, but just to be specific. And we'll just use a standard xy coordinate system to place the circle so the center is at the origin. Okay, just trying to specify things. Maybe at some time t it's over here, maybe it's moving in this direction. So here is the rate is distance. So if you look at the position vector is length r. So position vector is very easy to tell. It's r in that direction, and this is theta. So magnitude of position vector is r, but we have a trouble in saying, okay, this is the direction. So this direction is called radial direction. It can keep going in that direction. So that's called radial direction. And then there is a direction which can be perpendicular to that. You can see if the velocity is pointed in that direction. So this is the direction of the velocity. So this is called tangential. So let me draw it again over here. So sometimes I draw a very nice circle, but sometimes I don't. So these are the coordinate x and y, and over here, and from origin onward is radial direction, and I go tangent to this in counterclockwise direction. So if the object is moving this way, I don't draw this as a tangent. I draw this is tangential direction. Direction using notation is counter clockwise direction. So analytically, the direction is given by unit vector. So if I had a, if you remember, in x direction, y direction, so direction the positive x is given by I hat. What this is a special type of vector, and its magnitude is 1, and direction is positive x-axis. There is similarly a vector this way, j hat, and j hat magnitude is 1 and pointed to the positive y-axis, positive x-axis that way. So if you had a vector just of magnitude 5, say this was 5 meter per second velocity, but it was pointed in x direction, so this vector will be this velocity, let's call it v1. This velocity will be just 5 meter per second times I hat. This is a product. It's going to be a strange product. You can't multiply it. There are two different properties, this direction and this magnitude. Now, if I had a vector v2 in that direction, but still was 5 meter per second, then it will be v2 will be 5 meter per second magnitude, but the direction will be minus I hat. It will be flip that side. So this side will, unit vector will be minus I hat. This side unit vector will be minus j hat. Things like that, okay? So we know we have that kind of direction notation. We can use vector for it. So over here, similarly, we can say, radial vector, this radial direction, this is where it is at time t. And we'll say this direction, I'm going to pick a vector, unit vector, and you're going to just unit vector, use symbol u, but for radial, we're going to use symbol r for it. So this is the direction. So if I were to write, just like here, so if I were to write this vector from here to here, that vector, that distance is r. So position vector at instant t will be r, which is constant. U hat r. So where did the time go? Well, time must have gone in here, because if this object went over here, now the radial vector will be pointed that way. This is new radial direction. So the radial direction is from O to wherever it is. So this radial direction changes. So this is actually becomes a function of time. Now, one way to see it, I want to do circular motion in a natural coordinate for circular motion, and that will be the r direction. This r equals to r, and for direction you could use theta, which was the polar angle. So let's see what comes about it. So I have over here this point P. At point P, at distance r equals to r, and direction is there. So when you use theta, and it at point x, y, and it's going in x square plus y square equals to r square. So this is the circle is going in, and it's r, radial is r, but theta is changing in time. So theta is where the function of time comes in, and this is changing in time, and this is changing in time, such that this combination remains in a circle. So this is a constraint. This will say there's a constraint here. X and Y are not independent, they're connected by that. If you look at it using R, which is capital R, you can write down this as R cosine theta. So this is equal to X. So X of t is, so theta is, of course theta is changing with time, right? It's going different direction, different theta. So if some of the time is over there, so theta is changing in time. So let's for the y will be R sine theta. Very nice. So let's summarize. So we had a x, which was at time t was R cosine theta at time t, and y is R sine theta t. So we want, you can see that this vector at time t can be written in two different ways. Like before, we had xt I hat plus yt j hat, or in new way we have r u hat rt, r u hat rt, the radial vector. So either way you can write down, but we can express this guy a little bit more explicitly in terms of r. So this is r cosine theta of t I hat plus r sine theta of t j hat. And when you compare this with that, you can see taking the r common, cosine theta I hat plus sine theta j hat, just dropping the t dependence indicator just for simplicity. So this thing is this unit vector. So u hat r is simply cosine theta I hat times that plus j hat times sine theta. Is going to be important. And the time depends. This is time dependence, this is time dependence, this is not time dependence, this is not time dependence, this is time dependence. Okay, now let's look at the, we got the position. How about the velocity? You remember velocity is always dr dt. So we can do a derivative. Okay, so let's do the derivative. So you can do the derivative of this guy, or you can do the derivative of this guy, and you can derivative over there. So let's do it out. So d dt. So one direction, let's do the top direction of r cosine theta I hat plus r sine theta j hat. This is the only place t is. This is the function t is. So this just becomes minus, take r out, minus sine theta times I hat d theta dt plus cosine theta times j hat d theta dt. So you can take the d theta dt out in front. So you get r d theta dt, and then you have minus I hat sine theta of t plus j hat cosine theta of t. Now what is this? So over here, let's draw it again. So I'm over here, this is theta, and this side is, let's look at just one. So this is the radial direction. So this is cosine theta. This is sine theta. This vector over here consists of minus sine theta along that direction. So bring this over here. So it is minus sine theta here, and then this thing is cosine theta over there. I think it, let me redraw it. Redraw it very nicely. Let's say theta is 30 degrees, okay? So I'm over here at 30 degrees. So this is cosine 30 degrees is going to be square root of 3 over 2, and this is half. So I go over here and I do half here, and then I do a square root of 3 over 2 over here. So this vector will be, this will be the radial direction. You had r, then this will be this vector. So this vector is actually, if this is 30 degrees, then this guy is 30 degrees, and this was 60 degrees. So this thing is 90 degrees. So this is going back in our tangent. This is of course 90 degrees. So what this direction is telling me, this direction is actually the tangent direction. So this is and it has a unit magnitude. So if you look at what is the magnitude of this vector, we're going to denote this by u hat theta per tangential here. Okay, so u hat theta, if you look at the magnitude, that it's going to be square root of x part, which is minus sine theta square, plus the y part plus cosine square theta, and this is just 1. So this is a vector, is unit vector, and that means can be used for just direction. I just multiplied a quantity, so this velocity is this magnitude, and it pointed in that direction. Okay, so in a circular motion, v, through the process of 1, we got r d theta dt u hat in theta direction. Sometimes we say d theta dt equals omega, and you can say, if this is r and this is theta, then it has actually gone, this distance is arc length. So r is, you can write it another way, d dt r theta. So this arc, that's how much it was at t0 was here. It has gone that far. You had theta. So this whole thing is actually very nicely ds dt you had theta, and this is the actual path it has taken. So this is the speed. So speed at instant t, you had theta, which will also depend on t. So both of these are time. That's the v using path 1. So using path 1 through using this way of thinking of the position. Now let's look at this way of thinking with the position. This should be give me the same velocity, right? So using 2, this should be equal to d dt of r u hat of r. This doesn't have t, but this is a t. So let's look at what u hat of r was. This was cosine theta t I hat plus sine theta of t times j hat. So if I take a derivative of this guy to figure out the rate at which it's changing, this will be minus sine theta d theta dt I hat. But when I take a derivative with that, I get is 0. So this is coming from first term. This is 0 since d I hat dt is 0. And then I do over there, I get cosine theta d theta dt j hat plus 0, and this because dj hat dt is 0. So here I see d theta dt being common, and minus I hat sine theta plus j hat cosine theta, right? This way, I know this is a lot of algebra, but you have to really go through this algebra to see this thing in gory detail. So this will be u hat of theta. So it turns out that if you take a derivative of this thing, you actually get tangential. So putting in there, this just turns out to be r times d theta dt u hat theta, which is same. All right, so now we have a velocity vector which looks like d theta dt u hat theta, which is same as speed times u hat theta. Let's draw this out in our circle. So I'm over here at time t, and I'm going this way. So this is u hat theta direction. That's the tangential direction. That's the direction in which velocity is pointed. So this is the direction in which velocity is pointed, velocity vector. Now position vector was pointed in that direction at time t, but the velocity pointed that direction, and has the speed v, and everything's hunky-dory here, right? So let's do the acceleration in the circular motion. So acceleration is the time derivative of that. So now acceleration is going to be dv dt. So we need to take a time derivative of that. So we have 1 term, 2 term, 3 terms. So this has a time dependence, this has a time dependence, this does not. So this just will be r d square theta dt square. U hat theta of t plus d theta dt du hat dt. Now I need to find what that will be. So u hat theta was right over here. U hat r is this. U hat theta we have this. So let's start with that. Minus I hat sine theta, which is t, and no t here, so that's the only derivative we're going to go. J hat cosine theta of t. So the t variable is only here and here. So if we take a derivative of du hat theta dt, u hat theta is just the name of the whole thing. So it's going to be minus I hat cosine theta t d theta dt plus j hat is going to be minus sine theta of t d theta dt. So let's write down here what negatives is common. Negative is common, and d theta dt is common. You get a cosine theta I hat plus j hat sine theta. But this is just the radial vector. This is the radial unit vector. So minus d theta dt u hat r. So using that over here, this just turns to r d square theta dt square u hat theta. So this much along the tangent, okay, plus r, and this is d theta dt, d theta dt, so that makes it minus d theta dt square u hat r. So this is along the radial part, and this along the tangential part. Other ways of writing this, let's see, put r inside here. So d square r, I can do that because r is constant, you can place anywhere. dt square u hat theta, and I can write this as omega square u hat r. Now this is just r theta is so this will be d square s dt square and then this is just a ds, and dt is just the speed. So this just says how the speed is changing, not the velocity. So this is the speed. If in circle, is it uniform, or speed over is here, and over here is speed is way bigger like that. Maybe over here is way bigger than like that. Over here slows down maybe, or speeds up, but over here slows down, maybe it's like that. So the speed may be changing, then that's what this captures, u hat theta, and they're all tangential, and this is capturing what's happening radially, acceleration wise. But omega d theta over dt, if you multiply r here and r here and bring r inside, then you have a d dt r theta, and that just s, and this whole thing is just the speed. The speed equals to r omega. So we can write this a little bit more. So you have a dv dt u hat theta minus v square over r u hat r. Now let's draw pictures of what this vector will be. So I'm over here. V square of r is pointed in the negative u hat. So u hat r direction is that way. Minus u hat r in that direction. And so this much is in that direction towards the center. So this part is towards the center. So we'll call it centripetal acceleration. And sometimes you write down EC equals V square over R. Just the magnitude part, and direction is minus u hat R. Now this guy, tangential direction is u hat theta. So this is your theta is a positive here, and velocity increasing, then if it's speeding up, then this part will be there. So this is tangential, so it's called tangential acceleration. So it's point like this. If dv over dt is positive, and we say a tangential is dv over dt, and direction is u hat theta. If dv dt positive and direction is minus u hat theta, if dv dt is negative. So we can just include magnitude, just absolute value here, and we can direction, we just use it like that. So now let's recap. So in circular motion, equations will be position will be given by position. So at instant t we're looking at when it's pointed at towards angle theta. Okay, so this will be just u hat r, it will be xt I hat plus yt j hat, this is equal to r I hat plus sine theta of t j hat, and this is same as u hat r of t. So this is where the t resides, and the velocity is going to be v of t. It just let's go back, make sure we got velocity is r d theta over dt u hat theta, which can also be written as r omega u hat theta, which is same as speed u hat theta. So a whole bunch of ways writing velocity. And acceleration is going to be, it's also instant t, is is going to be a centripetal acceleration with a minus u hat r direction, and you're going to have a tangential expression. Oh, let's look at theta. Use the u sub theta, a sub theta, and the direction would be, so these guys have time here, have time here, have time here, and u hat theta t. And AC, this part is v square over r, and also written as r omega square. And this part, this thing a theta was dv over dt, which is same as d omega r dt, and r comes out, so r d omega dt is a whole bunch of ways of writing the same thing, r d square theta dt square. So in different problems you will have to separate it out. So if you have a problem, I'm not going to do any problem this session, but the next session I'm going to do some problem. So you have a problem, you say acceleration is pointed, has some magnitude 5 meter per second square, and it pointed towards radial direction, inward. Okay, given this, then I know what this looks like. So this looks like a centripetal minus u hat r plus a tangential u hat theta. So this will just be that guy, and this will be 0. So this a theta will be 0, and a centripetal will be 5 meter per second square. So just how you compare